So good morning. Today I'll see if I can take you to our workshop and see practically how we can make a small unit which will be similar to what I was trying to show you last time. I hope you recollect this box. Now these are all existing products that I've shown. Instead, I'd now like to go back and see if one particular unit like this can be fabricated. Okay. You notice here that it is similar to the other boxes which I was talking about, except I just, for our convenience, I try to copy the same I have all the three views of it. Don't get worried about is it first angle, is it third angle, is it as per DIN or is it as per the American system or anything. Just for me, so that you can understand the proportions of this particular product. If you remember earlier, I spoke to you about saying this could probably be a front panel. Then this could be probably be a top. Then this is the rear. Then this is the bottom. Having said all these things, I'd like to have some dimensions associated with it, saying in proper proportion. So, if you remember earlier, now I'll remove this by hand. I want a box which is about 65 mm, and then typically the height could be about 40 mm. And the top portion could be around 35. Then I have a small step which is 10 mm here, and then something which is as wide as 70 mm here. Intentionally I have not put arrows. I have not talked about is it an external dimension or is it an internal dimension. Now we come to the important aspect of how do we split this box. Do you have a top and bottom? Which length belongs to where? So I've had a talk with the workshop people and they've told me, while this is alright, if you can follow this, saying it probably makes sense if I make a top which is approximately like this. The same 10 mm what I have here gets carried here as 10 mm. That same 35 mm gets carried here. At the back there is a 40 mm. Plus the fabrication person has suggested that I also give a small wing here. And then as before, this continues to be 70 mm, this continues to be 65 mm. It's a little crude because over the years I have lost the capacity to draw straight lines on a board. But if I have a proper drafter and all that, it's possible. Luckily for us these days, I can very easily use a computer and get all these pictures on that. Now come back to here. You see here, this forms what I will call the base. Okay. Now following the same thing on the other side, I have a cover which closely follows this, like this. See here, approximately follows. Here also the same dimensions are represented here, 10 mm, then there is 35 mm, then there is a 40 mm here. And one dimension which I have intentionally left out here is this particular dimension. When we are laying out the sheet, obviously it's easy. We just need to mark this and then mark this. After marking this 10 mm, I join these two, 35 and 10, and then it comes automatically. However, when I want to spread the sheet here, using some usual geometry calculations, I need to calculate it. At this point, I'd like to add here from various what you call practical purposes. This has been made into 135, that is 90 plus 45 degrees. This is the one which I was talking to you about, how inclined planes are made and so on. So we have two units here, and then depending on the what you call our strength and the amount of quantity we'd like to make, probably I need to make two small openings which I can use for closing the cover. I need to make the small openings to make the cover in a very simple what you call unit like what I have been showing around. It is conventional to use a simple self-tapping screw. You just take a screw and then I just tap it, and then usually self-tapping screws, that looks too small. Anyway, I'll get one in the workshop, I'll show you. Advantage of self-tapping screw is you just need to make two holes, put everything together and make a small pilot hole, and afterwards you can just use it and then the whole thing gets covered without any problem. I'll stop here. After going to the workshop and looking for material, we have found out that probably a 1.4 mm thick material will be suitable. 1.4 mm aluminum alloy. This you will best understand if I take you to the workshop and show you there how we end up with saying what are the wanted dimensions. Would this be the external constraint of the box, or would you want it in internal? And the moment you have this 1.4 mm, whichever way you look at it, if I were to fix this as 70, this internal dimension will be now 70 minus 2 thicknesses. Similarly, if you have put 65 here, once again this internal dimension will end up with 65 minus 2 thicknesses, which is still an issue. So, in fact, to make our things easier, I have asked my colleague to help me with make one sheet. This is sample sheet. I'll say, and the what you call drawings are there. What the sample sheet will do is he will take a cross section across this. So I have 10, 65, 10, 10. Oh, we have ended up with this problem. Saying now, is this external or internal? Is 65 the external dimension we want or the internal dimension? Same way in the other direction, I have a 40 mm in one direction and length of 70 mm in this direction, and again 40 mm in this direction. The physical properties of the material and the physical conditions in which the fabrication is carried out has precedence over a simple equation. Even if you go to the best professional sites, one of the things they say is blank calculations are only indicative. A lot depends on the direction of the grain, how well the material flows, what is the property of the grain flow of the material, and then the big thing about T minus, small t, r, and all the calculations are there, which anyway they are available on the lecture notes what we have. So from here I want to stop and we move over to the workshop. So in this, in the sequence of operations, one of the very first thing is, okay, mark out the blank raw material. Okay, so after a lot of calculations, we have come out with saying we need a sheet approximately which is 150 into 85. Only for the bottom piece. Now we have the top piece. Now we have, in this case, we have a 10 plus 42, that is 52, plus 80, 92, plus 30, 133. So we end up with something which is 70 mm wide, and all these various dimensions are there. So what is the people will do is, they will go near what is called a huge shearing machine. They don't cut them anymore. You don't take a tin cutter, which you would do in the case of hobbies. Instead, we have a shearing machine. You need to mark out this. You need to mark out this on a large sheet. So what they do is, they take it to what is called a height gauge. We go to a proper, what do you call, a surface, a reference surface. I'll show you what it is. The one we have is an oiled granite marking plate. So on the oil marking plate, they keep a huge that basic raw material, and then if this is to be the basic raw material, usually raw materials come in the size of probably around 1 meter, okay, by 1 meter, 1000 millimeters, and they need to square up one corner. You will square up a corner. Then after that, he'll start marking, depending on how you would like to make. A first mark here and one more mark here. Now, we need to take it to the shearing machine, cut along this line and cut along this line. So in the end, we will have a beautiful raw material to start. So we'll now move on to the workshop from here. Thank you. So you see here, this is an oiled granite small surface plate. Then we have angle plates there. This one is a large thing, and this is the height gauge. Height gauge is nothing except that you have a nice reference surface. Then there's a knife edge here with a small step, and it's a dry zero here, and then it's possible for us to adjust it. And as before, we have a vernier, then we have a vernier screw setup. So what he does is, he's trying to make a small trial thing which is around 10 or 20 mm wide, and as per the total length. So he has set the marking here. He first locks this, then after that he operates the screw and ensures whatever dimension you want is made here. Now he has marked it at 10 mm. Now you see here, he will keep that plate across it, and he has cut it there. You see those two marks? This is a blank which has cut from a larger thing. So you can see that there's a mark here at 10 mm, there's a mark here at 10 mm. This total is 85. We have an 85 mm sheet, then it's about 25 or 30 mm wide. Now we'd like to see, depending on how we bend it, what are the total dimensions you get, what is the internal you get, and what is the external we get. Now he is trying the next sheet. See, once again he sets the desired dimension. Use that small screw so that in steps of 0.05 millimeters he'll be able to locate the. So he has made one mark there, he has made one more mark here, and we have a sheet. Seen here the 30, this is only a test sample to see how well all the dimensions we have marked here will come out in that. Stop. This is typically a folding machine with fingers. So see here, the one part of the jaws can be modular or split in this thing, starting from around 10 mm all the way up to 180 mm. We have fingers which we can adjust. Advantage being, in case already a sheet is bent like this, we can keep it here and put it there. Theory later on I'll explain. What we need to do is,
this radius will be,
there is a small radius here. Okay, any sheet we bend and all, the radius will be following this automatically. See, what he'll do is, now he'll try to, as per the marking, he'll try to locate it there. You'll notice here in this case, we mark the clamping line and not the bending line. That is the edge of the clamping line. And though he does it by practice, square, where is the square, sir? Normally they take a square to make sure that this is perfectly at 90 degrees. You have seen here, very little error is there. Okay. Now it will ensure that we get a proper, what do you call, then we have something which clamps it here. So we have this marking of the, what do you call, the clamps. Now he is trying to move it up like this. In the case of small job shop and the normal materials, obviously precision is required, and then you see after bending is completed, he'll check whether it's 90 degrees or not, and he'll compensate for any spring back or short limb has come. So it looks like around 0.3 mm error is there in the open length, and then he has now adjusted it, and he'll now one more time he'll check to see if it is perfect. See, it is reasonably perfect now. Now he'll try the other side. He'll now go a little faster. Now comes the critical portion of checking. What is this external dimension? What is the width that has come and what is this which has come? We are interested in the external. Now we need to worry about what is the thing. He'll explain to you. In the case of soft material, it is like this. But you see here, some of you may have seen such items. This is taken from an exercise cycle which is used for tensioning the band that is there, the brake band tensioner. Obviously, this is very thick. This is something like 3.2 mm steel sheet, and then all these things are designed for power. So in these cases, you need a regular power press. You can't do it with a hand press. So you have hydraulic bending presses. We also have very complicated forming of the thing. And if you see carefully, this piece is one piece. Okay, but this outside there is almost a 180-degree bend to economize on the material there. This 180-degree bend will make sure that overall things are very convenient. And then you see here, there is something in this direction, there is something here, there is something here. This is all done by special purpose machines with heavy loading of the things. And if you are to attempt something like this, it may not work easily on a simple folding machine. But this is a thing which is required for us. So still it is in that raw cement condition. They not have the beautiful blue color and the color pictures like that.
Still they are fine.
Saka?
Anyway, we do that. Let us
சொல்லி எழுத போகிறீங்க.
இங்கே எழுதணும்.
రివర్స్ చేసి ఇక్కడ మార్చాను. ఏమొచ్చింది? See, I have a few samples which have been lying around here. While these two are easy to manage, you see here we have a clamp which is peculiarly in the shape of a Z. While in a symmetrical section like this, we can talk only about the internal or we can talk about the external. We come into a certain thing here where external is here, we have a combination of internal, and then it's not easy for us to determine what is internal here. So at one point this is internal, this point is an external point, and this is an internal point, this is an external point. So this is the reason why we need to work about and learn how these things are made. You have seen this? Very easy to talk about an internal, or we talk about an external, but in this case part of it is external and we take this dimension, full thing is external. Now how do you get the internal dimension? While this is easier to manage, now we come to a very critical thing. This is part of the door lock which you use everywhere. Not very easy to fabricate such a unit, because you see here this one is long and these dimensions are separate, and then there are some special openings here, and as if that were not enough, there is also a embossing here and there is a fold over here. Now we need proper strength. So in this case they have selected the limbs and the thickness such that it overlaps here. I am still interested in the internal. There is a small thickness overlap here. Okay. In the case of mild steel, welding is possible, but when we want to work with these materials with aluminum, it's not as easy as it thinks. Okay, it's a very two thin sheets like this. They have been joined together. Two very thin sheets here. You see here, this weld has been made a little deeper, so it has come onto the other side. And you see, if you don't want any build up on the inside, you can probably just weld it on the outside. This is done with a loosely we call it arc on arc welding. So we have a shielded, gas shielded arc welding. So in this case, to prevent oxidation, we have a arc which is filled, and again both types are there. One is you have a wire feed inside which has the flux as well as the raw material, or it can be just a tungsten shielded arc. So in this case, I'm not sure, you see these two welds have been intentionally made such that the thing doesn't come outside, but we have a beautiful filleting here. This comes on both sides, which is probably stronger. In that case again outside. So it is for us to decide which way we can do. Simple shapes can always be, even these fairly complicated shapes, we can always make out of a single sheet. You see the way they have been laid out, and then there is no relief given here, there is no notch given here. So you see that it is shear formed, it is sheared and the same operation has been formed. Well, it is easy for us to talk about, we can even make this formation. How does it close without spring back? Even today, life is a little not that easy. See, you see here something which has been fabricated as a one-off sample in our workshop. See here, there is very nice T-shaped the thing here, made out of a single sheet. You see, it's a thin sheet. So it has been spot welded here, and then after that, this thing has been done by folding over. It's a little like the sample which I have shown you here. Sheet thickness has been done, and because of the various things, it's stiff, quite stiff. You can attach things together, and after all the fabrication has been over, they have taken a lot of interest and finished it by giving it what is called a non-reflective black color. So it has multiple functions. We also have a small mounting plate here which has two small limbs here which will make it stiff. Do we need it in all four directions? No, because most of the force comes here. And then we have a reasonably good enclosure with reasonably good joint faces here. After bending it over, probably they have put some bit of welding they have carried out. Now you see something which goes matching with this. Seen here, we have a device which I do not know whether it sucks in air or it transmits something or it is a heat sink or something here. So we have a perforated sheet, and instead of directly fixing a perforated sheet, they have used washers here to make sure that they locate properly, and then out of various constraints. And in the earlier thing I was talking to you about, how do you attach two things? Do you use a self-tapping screw or do you use a different type of a screw? You see here that this is called a riveted nut. So this nut is kept inside, and then we do a swaging or different type of an operation. And then the main attraction being, once you assemble both of these together, to start with it's quite a close fit and it becomes flush on the surface. How do you ensure it is flush? If it is a professional multi-made thing, we can make a step. We can make what is called a joggling step. But in this case, they have found it convenient just to make a simple formation and add another thickness to make things easier, and then also ensure that there is no gap here. They have taken it over after making the four bends, have left a gap here. The attraction of this is, overall, this will now become a generally splash proof equipment, so that in the unlikely case of some liquid flowing in at something, still it doesn't trickle in through this gap. This gap here does not matter. And then you see here they have made a hood also, a small hood, which shows that depending on your IP protection, if you are in this IP 55 and such things, at up to 45 degrees inclination, a normal water will not affect that thing. Hence, a small hood has been kept here. Now you may ask, won't it go through this? Yes, there's every chance of it. Contrary to our popular this thing, not all of them are air and watertight as we expect them to be. So I'll now stop here and take you to another place. What do you call a low volume, a flexible manufacturing thing. This one is called a horizontal machining center. While the inside and all is complicated, I'd like to point out that several of the features here and all use the same techniques as we use here. You see here, this is simple sheet metal, this is sheet metal. And then you see here, even here, there are small gaps, and it's very, for practical purposes, even if you shake it, you cannot dent it. And internally also, internal to the machine also, you will notice that parts of it are still made out of the same sheet metal what we are talking about. You notice here, inside I have several mounting details. I have a cover here. I have all this. These continue to be the same old sheet metal which you have shown there. Now, this is a simple, very beautiful sliding thing. You notice here, you see this corner? All this is made out of similar flat sheets. Only thing is the raw material, the finishing and the things are different. You see at the bottom, this one is our hydraulic circuit. It has a cover. In this case, it really doesn't matter whether it shakes a little. So what they have done is, they have made it in a simple way. While this is a horizontal machining center, you have a vertical machining center. You have a VMC. Even this VMC, several of the things, these are all sheet metal work. But here you will see that this is rounded. Using special tooling, they make the things rounded. This is a normal control panel. It's a mixture of both of them. You see this very effective, simple things they have kept here. And now I'll get back to you for the various types of hydraulic and control devices here. These continue to be sheet metal. And then you see here we have a a perforated sheet here, which probably has a fan of some sort, which will take things and take it out, and then you have a box there on top of it, which again has a power input module, and so sheet metal will never go out of fashion, and that too flat sheet metal is unlikely to give a problem, and it continues to make use of it. So I'll stop here. I want you to rewind this video clip and watch it carefully again and see as much as you can observe. This is not about how to use a machining center. See, all the sheet metal, that printout and all what I have done, I showed you, has been started here. Once upon a time we were using regular, what do you call, drafting machines. Now these days instead we try to build these things using some sort of a tool. Right now it is still it's a three-dimensional line drawing, so it will permit me to move materials around and then adjust something, and then depending on the type of assembly technique, it is possible for me to make a full three-dimensional model. And in case of any problem with the dimensions, you see, watch this 42.4 and then you see this 35. Now I will go to the side view, I will see if there is, let us say something happens and I am not able to accommodate all the materials inside. If I just want to increase the height, it's just enough for me to pick one of these things and then take it up. You see here, instead of 40 I have not made it 50. Conveniently this has become 35, this has become 50, this has become, and both the parts track each other. Now this top portion will fit there. If I undo it, you will notice, watch again, watch this 50, watch this 50. If I undo it, see here, this is 40 and this is 42.4. I can keep redoing and then play around with it. Let us say the height has become an issue for me. Very easy for me now to go back. Let us say the width has been the issue. I now make this. You have seen this. Conveniently, this is all become into rounded numbers. I have a 40, I have a 50, 70, and at the moment, they still continue to be lines. Very easy for me to convert these things into surfaces. I can make it into a surface using edge curves. So if I use this, I'm sorry. Pardon me, I have not practiced this. See, I have a surface, the first surface that has been built here. See, this is last point. I need to just build this next surface. See here, so part of that unit is getting ready. Only thing what you have noticed is it still has a zero thickness. Zero thickness will lead to all our bending problems. So I'll just see what best I can do, whether I can make these things. See, part of my enclosure is getting ready. Now if I were to just hide all this, you see here, I have all this ready. It's easy for me to now join these two things by, various options are here. In this case, for convenience, I'll just group it. I'll make a copy. something from here to here. I have a reasonably fitting bottom part of the unit. Now I'll one more time, I'll now go back to the other portion. I'll see if I can, sorry for the bomb. I have a beautiful bottom and a top portion of these things, so I can just either join them or weld them together, or depending on the type of thing I'd like to have. My enclosure is about getting ready. The advantage here is I have not actually fabricated anything and made a mistake. I'll get back to you again after that measurement point of it. So I have the top cover just to be on the safe side. I'll just see whether the top cover fits or not well. You see, I have a beautiful small enclosure. Actually the issue why I am showing you all these items is that from a drawing like this, it's easy for me to now make a development drawing. So what I do is, for the minute I'll hide this. I'll start with this bottom, start this, and you see I think there's a small error. It's depending on the sequence of bends. I can now make it lie flat in the other direction.
So what's that?
No, still a lot more is there. Last one is there. Almost over. Yeah. Now if you come back and see this. You've seen this? I've got a beautiful sheet which is laid out. It is possible for me now trying to optimize how these things can be made out of a sheet metal press. If you remember, the last thing was this workshop practice where I started you with this conceptual box. I have a bottom piece which has an inclined front panel, and then I have a top cover which goes in front of it, overlapping it. It overlaps here, overlaps at the back, and then there should be two openings here. But in keeping in the best traditions of blank design, we need to start with the actual bending elements which you need to give. Contrary to popular belief, there is no equation for the bending elements. What we have is physically we need to check what is the bend that we take. So our operator here, after calculating this 40 plus 70, he has come to 150 mm. So this is typically the 150 mm blank that he has taken. Similarly, the other one is after taking this small length of 10 mm, 10 mm and 65, he has come to this 85 mm. Having done this, we now need to carry out the bending operation. After carrying out the bending operation and taking a measurement using this height gauge. Height gauge is nothing but basically it's a vernier, except that it's a lot more precise on how it is mounted and so on. We have these angle blocks, then we have the surface plate. In this case, for the purposes of it, they have cleaned off the surface plate. Normally, it will be a granite which is oiled specially. This is a little spoiled, but it's okay. Having done this after measurement, what we started with, this marking of 150 mm by around 20 mm and 85 by 20 mm, if we measure the limbs, we now come to a very peculiar thing. This 40 mm has become 42 millimeters, and 40 mm has become 42 millimeters, 70 mm has become 72 millimeters. Suddenly, we notice that in spite of marking the internal thing, something what looks like an inexplainable extra 6 mm has come out from somewhere. This is what is part of the behavior of the metal. So today, my colleague will continue with a more real life example of a unit which will be quite useful. Compared to what you did yesterday, which was a simple U, this is only to find out the bending allowance that is there. The two types are there. One is if you take the external dimensions, we do subtract a material which is called the bending deduction allowance. Otherwise, we take the internal and then after that we add an allowance. Now we will come to a real life object. In this case, this is called a hat section. This appears slightly more complicated. The reason being, what appears outside, inside and all that, those dimensions, internal, external and all that, out of practice, these people will know how to take the outside dimension, remove two thicknesses. Similarly, in this case, same, take one of these things, remove one more thickness and come out with all these things. This is a generic product. Loosely we call it a hat because a cross section looks like a hat. In today's second real life example, my colleague is going to try to make a small mounting arrangement which is probably used for an antenna. See, the important issue here is all the details that are required here in the final part are already marked out here. And compared to yesterday's system by which we mark 10 millimeter from both sides, which is a little problem. When you work with a height gauge like this, what we need to do is we need to mark out dimensions as they come fair from the bottom to top. So as before, he will release these things, start reading out this and marking it one by one here. So the advantage being it's all based on a datum line. And if you follow a CAD or even otherwise hand drawn things, making references from the datum line is very convenient for us. Mainly because in the flat condition we also need to make all the perforations. In this case, the large hole has to be blanked out. Any hole which is more than around 2 to 3 times the thickness are best punched. Small holes can be drilled, otherwise the best operation for it is if it's a let us say 2 mm sheet, anything above around 8 or 10 mm cannot be drilled. If you drill it, it leads to a lot of problems. So now I'll stop talking, we will start concentrating on the marking out. So in the initial stage, what he has already done is he has cut the sheet, he has prepared the sheet to the necessary thing 88 mm, then towards the length, and then here also now is 326 mm. How did these dimensions come about? As before, they have taken all the necessary dimensions and then added and subtracted the various types of allowances, and then we have a sheet which is already cut and prepared here, and the sheet has been cut from a large material on the shearing machine we have there. So keeping all the safety things in mind and all that, in this case, this being a very ordinary, I won't say ordinary, demonstration piece and meant for students, you will notice there are a few bits of scratches and all here on this. See, our engineer has started, he has put the first mark which represents, in our case, a line which is the clamping line. The clamping line, using our finger type of brake, is the line along which you actually clamp the object. This line makes sure that any material which is inside the finger does not move. So, after that we have an internal bending radius, after that we have the sheet thickness and all that to get the external thing. Now, you see here one more time, he is now marking all the dimensions based on the datum line. See, the slight difference is, except for the symmetrical items which he finds it convenient, all others have been marked with respect to one of the edges. It is very, very convenient. Main advantage also being that in case you have a coordinate drilling or a coordinate type of machine, it is easy to program or read all the dials and check these dimensions easily. So, the standard operation in the industry is, at least the first few pieces, after the vernier marking is done, it is sent for inspection to see whether there has been a mistake in either the drawing or the fabrication. Why this is required is, we want repetition. If you make even say 10 pieces, it is worthwhile having the drawing checked against the first marking and completing one sample piece. Then in case there are any inadvertent errors, mostly caused by not interpreting the modification list or modification requests that have been made. Now, you see one after the other the fingers being marked there. You will notice that some of the essential features, especially relating to bending, instead of following the datum line, our engineer is marking from both the sides. Why he does it is, the throat depth which is available on our machine is limited, and the various features are best done in a sequence of operations such that, see what he is doing next is, he is doing the notching of the corners. And you see the what you call good thing about a workman is, he depends on his tools. Nothing is done just by eyes, looking at the eyes, no, we're okay, but still you see here, he is trying to use a square to ensure that the notching is perfect. You may notice a small error, but it does not matter, because even if the center did not follow the whole thing, it gets compensated on the other side. As such, there will not be a problem at all. However, in the case of production, generally what is called a front or a backstopper is used to ensure that it always runs parallel. Now, he has come to the notch of the second symmetrical bend on the same side. Overall, we end up with appropriate number of notches. He is an experienced gentleman, but in spite of it, he still depends on it. You will notice that for each bend, wherever we have one of these notches here. If you look back on our drawing for the hat section, the top two require this notching, because we have two webs which both need to meet. That is where this 90-degree notch is required. But then you will also notice the other two bends which form the basis of it, They don't have it because the bending is being taken in the other direction. It is done in the 90-degree direction. As such, even making a bend is not required. Instead, he will probably remove the material which is not needed at all. So, we have a flange. The total length of the flange, the corner is being notched off. While this is a general purpose 90-degree notching device, you can have it for other things, including maybe circular, including other angles and so on. So, I will call it the limb 1 corner notch he has removed. Now, he is coming to the limb 4 corner notch. So, that part which is between 1 and 2 has been removed. Now, between 4 and 5, he is trying to remove the material. Now, looking at it, you will slowly notice that this starts looking a little like the drawing that has been presented to us. You have seen here. Now comes the next operation of he is having to make a big opening. So, once again, our engineer is now adjusting critical stoppers. In the previous operation, both the operations we could see where the work is being done. In this case, it is not easy for us to find out where the punch is now sitting on the actual sheet. We need to depend on the stops to ensure the total dimension is maintained. So, if you observe this machine carefully, on the top I have a flywheel which gives a tremendous amount of kinetic energy, and then this is just a stopper to see that it does not go down and injure things. And then in this case, we have this is called a stripper. Stripper ensures, see, he has done a sample just to make sure that the opening and the location is perfected. You see here, he started from when it's put both the stoppers, and as per the original center mark, he is able to now locate the particular feature where we want it. That impact is the one that will give a clear opening. It follows the marking that he has done. And generally, if you see in the real life, more than the location from here to here, relative location between the 4 mounting holes and this opening is critical. Usually this is done by a template. Though in this case, he will mark and drill, it is done by a template, so that even if there were a small 0.1 or 0.5 mm error, it will not accumulate and cause a problem in the final product. Now, what the engineer is doing is, because there is a small change in this thickness, and this is the, if you remember, I was talking to you about the finger. You see here, we have a finger here. He needs to adjust exactly where he wants to mount the finger. So, he has just marked one line here, and then after that the internal bending elements, and after that the radius. These two are included in it, and then he has marked the clamping line on that. The rule being that whatever is held inside this will not change. And this machine, it has the lower two movable jaws, which ensures that the thing moves up. So, you see here, he is trying to align it as best as he can. Generally, for our purposes of demonstration, he is just trying to hasten it up a little bit. In reality, there will always be stoppers at the back. So, if you see here at the back, you see the stopper. We can move it up to that point. Now, because of the thickness involved, he is now compensating for the thickness of the sheet and the amount of force that is required to clamp the sheet. Now, we will operate both the jaws, lift up the portion, and you will notice that he is also checking for the spring back action. Is there a little spring back? Yes. all materials will invariably end up with a spring back. And now do we have to do it as a trial and error? Not necessarily. First time you need to make an empirical thing. At the back of it here, see, it's clean. On both these limbs there is a stopper there. You can see there are drilled holes there. He can adjust the stopper to make sure that it stays within the angle we need. Most of the times it is a right angle. Occasionally we have other angles for that. And because of the design of that clamping fingers, we have reasonable control on how well the thing it bends here. One small detail you would have noticed is, now if you see here the material has tried to form and shear also in the corner. In professional practice, they also provide a small notch, usually to equivalent to the thickness, depending on if you want this limb to overlap this, or if you want this limb to go off inside, this will be a little smaller, and the notch is done in the other direction so that it goes inside. So I will see what is his application. So you see here, these fingers come for different lengths. We see here they all come in discrete dimensions. 10 is marked here, 20 is marked here, 25 is marked here. So making combinations of this, it is possible for us to say this is a really wide piece. So what he does is he can remove this depending on whatever we have marked. Yeah, this is a 165. Show me the sample, sir. Show me the sample. So you see here, see, it fits reasonably well. So depending on our sincerity, the accuracy that is required, it's possible for us to spread them uniformly like this to make sure that both the extremes fit properly. But in this case, since the material is not very, dependent on local deformation, he is taking a small risk of making it just centered, and then I expect that up to 1 or 2 thicknesses it is safe. So I think in this case around 2 thicknesses worth the gap is there, and then with his little bit of skill he is now forcing it back into the 90 degrees. See, we are quite close to what we have done. It's nearly perfect. While I do the talking, he does the working, which is the actually perfect part of any work. Bending, the internal bending between the 2 and 3 are over. Now 3 and 4 he is doing here. This is where a small adjustment has been done without telling you. You see that these features of this depth here, the depth inside, have all been taken into account, and in fact he has provided a small notching to make sure that it does not hit there in the whole thing. You see, sequence of bends and such things are very, very critical here. They will try their best instead of fully closing it. Now he will do the next operation and see well how far he can take it inside and continue the operation. So in this case, this has opened out a little, but it's a harmless thing. We can always dress it back to shop. So whenever you use these general purpose tools, we have this little bit of compensation we need to do. Having done this on one side, now since the total length is a little less, you see here it seems to miraculously sit inside without any problems. So if it were a batch production, probably they will do it in 1 or 2 extra operations. And then we have something which is practically ready. You see here, now probably either you can manually dress it, or in this case a little clamping is even probably possible, and we have a nearly perfect operation, except that it operates little more in it. But in our case, this because of the springiness of the material, it is possible for us to dress it back into the original condition. You see, it is a little springy in this case. So as such, for our type of work, It's generally easy. Now, in the original drawing, we'll notice that we have 2 more openings here, holes, and 4 more mounting holes for this center feature. He has, in this case, sometimes these holes are probably need to be drilled and transferred to another mounting base. And then inside there may be other features of it. So, these 4 holes, these 4, he will now attempt to make it on this by taking it to the drilling machine. You see here, this has been part of the operation which they required. So, I will now take you back. Before he said, say, we have 3 drilling machines here. This one is a little fairly big one. It's a tapping machine. That is your standard workhorse. And then we also have a portable drilling machine for longer operations. Drilling and tapping machine. Then we have a thing here. If you notice, it doesn't have a chuck. It is directly, large things are mounted directly using a Morse taper. And in this case, we have a tapping attachment. So, this tapping attachment, when move it up and down, it will reverses and then makes the holes there. This is the conventional drill there. Okay. You see here, this is a actual bending machine with a V punch here. Even this V punch, in this specific case, we have made this long one non-piece, but you can have them segmented. Same thing, this can be segmented. All other angles less than 90, little more, incorporating swing bracket, everything is there. This has 2 operations there. There is a large lever there, and then we have a toggling mechanism here, which ensures due to the toggling it goes down, bends back. When we have a nice a long length which we can do, and we can progress them along. So, if you have a sheet which is, let us say, 2 meters, this whole thing is only 600 millimeters, 500, you can just moving it along and we can make it. Something matching with that is another low non-impact normal punch. In this case of normal punch, if you have small openings like this, and then they need to be a little precise, we can mount this in the die holder, we can mount this punch on the punch holder, and then afterwards carry out these operations directly by aligning it, and then we can make this small operation. So, what is required in a small workshop is probably a few of these machines. So, you have a small press and so on, and then you can carry out most of the operations that are required for a electronics thing. I now bring your attention to things which are all made. You see here, this is the sample we made yesterday. Okay, compare it to this, what we think is a little hard, this thing. This is made from a steel flat, and this is part of a bigger machine which where the accuracy is very, very critical. So, while an engineer needs to familiarize himself with all these various operations so that the design comes out properly, there are job shop people who continue with the various types of operations for you. But why we have, or rather I have put you through all these steps is that you should know the amount of various types of limitations of the process. So, while a drawing looks good when you make it, finally you need to compensate for the shortcomings of the press. So, thank you for today. We will meet again next time.